Good to see everybody here. Matthew's asking if I made that drone footage. I didn't. I actually I called the guy on the phone who made it, and it's a really cool video. I wonder if we could find it. So I called that guy on the phone, asked him if we could use it. So who is Jason? He was my editor. He still's around UT. If you ever see Jason around the Haslam College of Business, say hey to him. It's not Sunfear in Knoxville drone footage. Jason is such a great guy. It's not that one. It's not this one. I'm trying to find it. It was such a cool video the guy made. He was at UT. He was at the park, and he did some. It's copyright music. I gotta watch out. He has copyright music all over it. So I took off the music on it and just used his drone. There's new drone footage. I should check it out. But he's been so kind not to copyright claim us. So we've never gotten hit with a copyright claim, which if you use people's footage, they could easily hit you with a copyright claim. That's not it. That's a bummer. If anyone finds it, the guy, if you ever watch it, the guy, I'm seeing the Simpsons episode with Knoxville in it. I love that. Oh man, Knoxville 10 Sunsphere babe. Oh, that's so cool. Oh man. So anyways, he's never hit us with a copyright claim on our video, which I don't know if it would catch that because I have like an overlay. I did tell him I was using it. He said okay. Yeah, like I called him up. He's like, hey, this is so and so, and I was like, hi, I'm blah 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 blah. Can we use your drone footage? He's like, yeah, sure, whatever. That's cool. So if he ever like got mad at us, I don't know. We did get copyright claimed on a song I had playing over it, so that happened. But how is everyone doing today? Veda, good to see you here. Max, good to see you here. Wilton, good to see you here. Julia, good to see you here. How is everyone doing? Make sure to hashtag show up. I'm so afraid to look at the numbers. I know a lot's going on. Gosh, I had a crazy morning this morning. Probably I might have to like answer the door in a moment or who knows, because we're having a maintenance person come by. But it was an absolutely crazy morning. Anna, good to see you here. Number one thing, when things are crazy, you gotta just like you gotta like just I don't know, it's tough. If things get too crazy, lean on other people. Class, woo, I agree, Mon, right there. Let's throw out some more points to everybody. You gotta do some points to make everything good in life. Because I just tell you, some days, today's been one of those days I was just like, man, I just wish it was the weekend. And then turns out I finally got, if you saw office hours, which a lot of 474s had office hours, my apartment complex wasn't answering the phone. So I had to call the manager of the apartment complex. Let me speak to your manager. But I mean, they weren't answering. And it turns out they're at a conference. Lindsay, good to see you here. And so she said, oh, I have everyone at a conference in California this week. And thus no one's at the office. And hence why they weren't answering the phone. And so she's sending someone out to fix the issue. And I'm really happy that got fixed, causing me a lot of anxiety this morning. I was like, oh no. And then we couldn't get someone to fix it because they're not here this week. So anyways, that's what we got going on in the world today. I hope your day's been a little less stressful. The number one way to not be stressed is to show up to class and also to do the material. So we're going to hop back in here to the notes. Does anyone remember what topic we were covering? And I should invite my 201 to this today. I should have done that. That'd have been interesting, right? Because 201 has a test tomorrow night. And what we are covering right now is on their test. So we're doing some review. Who knows for 50 points what we are covering today? What topic are we going to start off talking about today right here? Who knows the topic of the day? What do we have? The topic of the day is what? It's me drinking coffee is what it is. What do you have in your notes from last time? Correlations, class 10. Let me fix that. Association part 2, class number 10. Let me go and change that. I'm going to go break the stream. Watch this. That's the morning live office hours. Let me go to live studio here. Class 10, good. Let's go to edit. Oh, no. Correlations part 2. We have 26. The numbers are still climbing. 26 watching live. We'll take it. We'll take 26. Correlation. It is correlations. And now look, correlations part 2. We started last class. Let's hop back into here into some correlations. Well, that's scary. This is an important concept we were covering in 201 a lot. Correlation only measures what? This is a thing you should know instantaneously. When you look at this, correlation only measures the what. So you see right here, all these correlations are equal to 0. And I tricked people last class, if you remember. Oh, yeah, you might just click refresh on the video. I changed the title of it while I was doing that in the background. Danielson, 20 points right there. Correlation only measures the linear strength. So when you look at the linear strength of these right here, the linear strength of these is all like a line does not well approximate it if I could draw a line. So linear is what we do when we do Pearson's correlation. You're going to hear a new type of correlation today, and it won't be Pearson's correlation. So do remember, things can have, mine changed. Awesome. I don't know why yours updated and others didn't. When it comes to outliers, what can outliers do? And you'll be doing this in your assignment. What can outliers do to a strong correlation, a weak correlation, a positive correlation, a negative correlation? Outliers can do what? We're doing some quick notes here, kind of review of last class. You should know outliers can do anything to the value of correlation. Hence why we say QQ, QQ, straight enough. No outliers. Veda right there, and Danielle's correct. It can change it. Everything basically is what outliers can do. That's why we don't want outliers, because they're going to dramatically change it. You'll be doing on your assignment coming up here for this, looking at how correlation can change with outliers. And the answer is it can do anything. When we have r squared right here, we want a very high value of r squared. What is the complicated formula to go from correlation? And this is review. What is the complicated formula to go from correlation to what is called the coefficient of determination? You'll probably never hear me call it the coefficient of determination again. You'll only hear me say r squared. Interestingly enough, 1 minus r squared is the unexplained portion, which is the coefficient of non-determination. I do see it capitalized sometimes too. But r squared right here, how do you get r squared from r? You just take correlation and do what? So when you have r squared, you just take correlation and what? Which is one of the ways to get r squared, I should mention. There are other ways, which we'll see in later chapters. Squared right there, Veda, again, some points for everybody. You square it to get r squared. Now, that means r squared, in this context, can only go between what and what values. And think, it's a percent of variation we understand in the y variable explained by the x variable. So it's basically how far we get to understanding y by understanding x right here. So the amount of information in y understood by knowing x. So r squared would go from what to what? R squared is going to have values that range up to 1, meaning 100%. And it's going to go down to what? 0. Be careful right there. 20 points. Don't worry, Joshua. Joshua, you are right. Joshua, your values are for what, though? Josh, the values you have right there are for what? Not for r squared, but Josh has the values that are possible for what? Not the values for r squared, but the values for what? And then think of what happens if you square these. Exactly, Joshua, another 20 points. Yep. So Josh, the values of r will give the direction. So if you look right here, the values of r range from -1 to 1, but when you square it, you will always get a number that's positive, because negative times negative positive. And so you will get values between 0 and 1 for r squared for the percent of variation. Exactly, Megan pointed out. Great notes. And these are things we want to remember. And just think, like, if you square correlation, it's positive, and then you get the percent of variation in y that is understood by knowing x. Remember, x is the explanatory. All this great stuff. Bunch of review right here. Please slow me down if we're going too quickly, but we like to review and get these topics down. So r squared is a measure of practical significance. How would we know if the correlation is statistically significant? And here, I'll let you see some correlations. Here's a bunch of correlations, and this is where we got to. How would I look to see if these correlations are statistically significant? So the slide we were just looking at, which was review, mentioned practical, but let's look at statistical first, because we always do. How would we know statistical significance? Right there, Megan, you got it, p-value. And so the p-value right here, and be careful, it might look like it's 6, but p-values have to range between what and what? Now, every time you see a p-value, make sure you know it has to be between these numbers. It looks like it's not, but I promise you it is. P-values have to be between, because there are a probability of our results or results more extreme occurring by random chance variation, given that the null is true. P-values have to be between what and what? I'm going to take a moment here, and I want you to tell me what is that p-value, because I can tell you, but a lot of people get it wrong. A lot of people don't know what this p-value is right there. They say, wait, that's a big p-value, and I say, no, no, no. And you are right, it's between 0 and 1. 100 points on the line right here. What is the p-value that we're looking at? Be careful. I think Matthew, great answers right there. 100 points, Matthew got it. I like Wilton's answer. I'm throwing another 20 points. The E is the key, exactly, because it's in scientific notation. The way to do it right here is if you count the leading 0, there are 5 zeros. You have to count the leading 0. That's the way I remember to do it. So 0, that's one of the zeros. 3, 2, 3, 4, 5. If you look here, there's 5 zeros, and then you would write the remaining. So that is the p-value right there. I don't even know how to write numbers. I know how to write zeros. Nothing. Other numbers I don't know. I think it's them. I'll go check it out in a second here. Sorry if I go, I might have to go check something out, like the maintenance people. So when we look at statistical significance, what could we do to the numbers we just saw on the screen to look at the statistical significance? You might hear like, maintenance man. I don't think they're. What could we do to look at the statistical significance on this screen? So going back to that screen, which is where we're getting to, if we want to look at the statistical p-value, if we want to look at the practical significance here, what should we do to any of these values? If we want to look at the practical significance between someone's attractiveness score and their face symmetry score, which is how symmetric their face is, what could we do to the correlation value to figure out the practical significance? And I'm giving you a hint by getting this ready. What could we do to look at the practical significance of that? Thoughts? And then we're interpreting this next. This is the applied and like your assignments. So what could we do to this right here to look at the practical? Boom, Wilton's got it. That's R. So let's square it. And by squaring it, we can enter in all those decimals. We got time. We got all the time. We got a time machine. So now, how would you interpret this? And we could multiply this by 100 then. So remember, we squared it and then multiplied by 100 because now it's R squared, which is a percent of variation. So how would this be interpreted right here? And it's basically this. I would just round it if I'm talking in reports. And remember, we're talking about someone's attractiveness score explained by their face symmetry score. Try interpreting this, another 100 points on the line. These are great test questions, and these are the ones people miss when we say interpret stuff. So see if you could interpret what I have here for R squared. Use the notes from the previous page. So if you have the notes up here, I'll show you. So it's face symmetry score explaining someone's attractiveness score. 21% of the variation in attractiveness can be explained by their just Veda right there. I'm throwing another 50 points on top of that. And so, Max, this will not be a slope. Good answer, Max, right there. This will be, and so Wilton has it right there, 21% of the variation and about 21% of the variation in attractiveness score is explained by the variation in face symmetry. That's perfect there. And I like to throw that extra explained by the variation on there. Or you could say, knowing somebody's, here we'll go back, does it right here? Knowing somebody's face symmetry score gets you about 21% of the way to knowing their attractiveness, their attractiveness rating. So knowing someone's face symmetry score gets you about 21% of the way. I like to say 21% of the variation, as you're seeing people write, stats 1 right there. 21% of the variation in attractiveness can be explained by the variation in their face symmetry. If you don't put variation, probably won't be so mad right there, but Veda and Wilton right there. Was that some stat 201 knowledge? I'm trying to remember. I think Veda took 201 with me, right? I think. Maybe it's just so far in the semester I'm remembering all the names. But that's 201 knowledge right there, and that's practice on R squared. So try another one right here for another 50 points. Let's do somebody's fitness score. I want you to solve now for the interpretation of R squared for fitness score. Take a moment. When you get to the test questions, you got this. Stats 1 going right here. Megan, everybody, let's do this. You got this. Go ahead and interpret this. I'm not going to show you the answer yet, but take a moment and interpret the R squared for fitness score, explaining someone's attractiveness score. Oh. Voicemail. 2 seconds. Sorry about that there, everyone. Apartment complex getting things fixed, and so make sure I sent them. They said they had the wrong apartment number. I'm going to make sure they confirm. There we go. It looks like extra clothes at the waiting video. You guys love the waiting video. I don't know what you're on, but I feel 22% of the variation in attractions can be explained by the variation in fitness score. Yes, right there. That is it. And let's take and solve it. 0.466970484 times itself. And there we get it right there. Does everyone see how we're getting that 22% right there? Phone call group right there. I'm hoping I put in the wrong number. Let me double check. Just want to confirm you have the right number. No. I texted the wrong thing. Sorry about something. I am crazy. Oh my gosh. I can't text. Attractiveness is the Y variable. That is correct. Alyssa right there. Sorry, just dealing with apartment stuff in the background. That's the fun from teaching at home. Woo! Apartment stuff in the background. So the attractiveness, the score right there is the Y variable of interest. So that is what we're trying to understand right here. It could be switched. It is true that you could switch them either way. Didn't even notice that joke. I don't even know it. I don't get the joke. So what we have right here is a correlation matrix, but we don't like correlation matrices. We want to use a all correlation code. Now, what does all correlations get for you? Just go crazy right here. What do you think all correlations get you? Who knows what all correlations gets you? Brian tries to calm down by drinking coffee. What does all correlations get you? It gets you all the correlations.
Wow.
All the correlations. But this code right here is a lot to look through. What if we had an additional argument, and the additional argument allowed us to specify a what? If we had an additional argument right here, and the additional argument allowed us to specify a what? The additional argument allowed us to specify the what? Megan's joke is so high level. I didn't. Oh, I get it now. I didn't read the first. I don't you. Megan getting her own 100 points right there. She literally sent a crying face emoji. She sent a. I think she got it. Oh my god. She said a crying face emoji. Please add the Kevin Garnett anything is possible soundbite on your soundboard for talking that, and I'll put it on there. And it sounds small enough that we won't get copyright claimed. So when we look at this right here, there's an additional argument. It looks like my apartment complex has the right apartment number now. Woo! Man, today's been crazy. So what is this additional argument doing? Look at the output, and I want you to focus in on this. Brian's going to focus here. And I want you to tell me what changes about this output when we do interest equals this. So look here. Here's without the interest. Here's with the interest. What does that additional argument do when we don't have the interest and we only have the interest? So it says interest equals score, and then what do you notice about without it and now with it? What is changing about this output? How would you explain what does interest do? What does interest do when you add the argument interest equals this? And make sure it's in quotes. When you specify the interest for the correlations, then in your output you will only what? When you specify the interest for the correlations. It often does that. Correct. Joshua, you are correct. Joshua, I'm throwing some 20 points. That's what it looks like. It makes sure that that variable is in all the correlations. So when you do interest equals this, just because score, I think, is one of the earlier variables, it is the first. It won't always be in position one. It is here. That is very correct. But every single correlation will be, it'll have that variable in it. Does that make sense? It only outputs the correlations involving the variable of interest. Wilton right there, perfect answer. And Josh, great start to it. It would look like it's always in the first position. That's just the way this output is. But Wilton right there has it correct. It only outputs the correlations that have that variable as part of one of the two. Does that make sense? So it only outputs the ones that have that as part of one of it. So it would be there in some way. But now we have sorted equals strength added on. And with sorted equals strength, it's going to go from negative to positive. The position doesn't matter on the last one, but it does here. Because now when you look at the positions here, this is the one that is closest to -1. And these are the ones that are closest to +1. And in the middle here, right about here-ish, you have the closest to 0. So if you look, this goes from weak or most negative to most positive. But even more importantly, let's go check this out on the main screen. All correlations is such a cool code because, and this is one Dr. Petrie wrote, if I know how to spell it. Make sure you have reg class on. I think that's them. Nothing like having work done while you're working. When you run it, it's too big for the output. Look at what you get. You get a ton of output when it appears. There it goes. And let's go here. I hate that we get that output. It's a graphical thing, and here's all the correlations. Can you sort by absolute value? You can, because that would be even better, Max. Max 100 points. To sort by absolute value, you can go right here and go sorted, and be very careful, equals magnitude. Make sure you spell it correctly because typos will not work, or it'll just take. And now look, when we're sorting by here, Max said, can we sort by the absolute value of the strength? And look, we are getting sorted by the absolute value of the strength by sorting by magnitude. You also have the ones with the smallest p-values down right here. And take a look. Is this obvious? What's most correlated with somebody's weight? The most correlated thing with somebody's weight, which we could only look at weight if we want by going here and going to interest equals weight. And I've shown people this code who work with data, and they're like, wait, what? You can do all the correlations of a data frame by looking through desired weight and number of body piercings? Why would number of body piercings be negatively correlated with weight? Why would number of body piercings be negatively correlated with weight? Video games is positively correlated with weight, and it's very significant. So video games, how funny people think they are is positively correlated with weight. People's GPA is negatively correlated with weight. Probably a lot of this, and we looked at this, I think, at the end of last class, is probably due to gender. Gender influences weight and piercings and video games to some degree. Now, my fiance and I were playing the Nathan Drake collection. It's so good. We're on Nathan Drake Uncharted 2. Great game right there. So we were playing that last night. 2's even better than 1. I can't wait for 4 because I've seen what 4 looks like. So, well, we can correlate piercings, and piercings is negatively correlated with weight. We generally see people who weigh more have less piercings. Less piercings, way more. And so, does that make sense, Alyssa? Great job right here. Just think about what this data is showing. We could also look at what's most correlated with piercings pretty quickly by switching this. And look at this. There's what's most correlated with piercings. And the most correlated with things with piercings are things like height, weight, all these things right here. And everything is statistically significant through here. There's a lot of statistically significant things. So there's a lot of statistically significant things. And it's very easy to run this output and just change, like, why do people think they're funny? The number one reason why people think they're funny is because they think they're attractive. Being attractive is highly correlated with being funny, and it's almost about 25% of the variation. We can get the R squared here pretty quickly by just taking this and squaring it and saying 27% of the variation in how attractive people think they are is explained by the variation in how funny they think they are. Then, oh yeah, sorry, I should add one more thing. Let me throw some 20 points. Great job right there following along. Run data, survey 10. Daniel, thank you so much for pointing that out. Sometimes I forget to run a code that I've already ran because I might already have it in the environment. But Daniel, thank you for pointing that out and running the code. We're throwing Daniel 100 points for following along, running the code right there. On this is var1, the x value. Either one can be the x or the y. A lot of times you would think var1 is probably a better thing to call x and y. But it can go either way. It just depends if you want to say which one is the x, because the relationship x and y have is the relationship y and x have. So you can switch them. But if you're trying to explain something to someone, it might make more sense to say the reason, or like, not the reason, we shouldn't say cause and effect. But there is a correlation between GPA and percent funnier, which is statistically significant. But it only is explaining only about less than 0.5% is explained of the variation in people's GPA is explained by how funny they think they are. Now, it is statistically significant. Yeah, actually, we could. Max, I'm throwing 100 points. Max asking right here, could we do that? Let's do this. Watch this. I'm going to store this by doing a right arrow and store it to a data frame. So I want to point out that you don't always have to left arrow. If I'm at the end of a code, I might right arrow just because it's easier to go and store it. And then I'm going to go here to data frame, and I'm going to go r squared. And we're going to store into it a data frame of the correlation, and we're going to square it. And now let's look at our data frame. And Max, check out what we have right here. Is that the r squared? I don't like that it's viewed that way. You know what we can do? Let's rewrite it here, and let's times it by 100. And then let's go here, throw it inside of a round. And then that's the first argument. That's the second. And there we go right there. There's all the r squareds. And that's why we code. Because, and Max, I want to throw another 50 points for Max. It's such a great question. So now we have all the r squareds. We don't have to worry about calculating them. We can just write code to get it, and then we could print this off, and we could even write code that tells us the answers. Because this is going to just find it all for us, and you can just see the r squareds decreasing, especially when you get down to things that are not statistically significant. One last thing we could do right here if we really wanted to, like if we were going to use this a lot, let's mention one last thing we could do, is we could go here and we could look at the p-value to see if the p-value is what. We could look at the p-value to see if the p-value is what. So what could we do right here? We could look at the p-value to see if it's what. Now, there's important topics. I know I'm coding a lot right here, but we could look at the p-value to see if it's what. Very important thing. So we take that p-value vector, see if it's statistically significant. There's the ones that are statistically significant. And let's go right here and go as dot character, or let's do this. If else, very powerful code. And if it's less, it'll be yes. If it's not, it'll be no. This is the if else, very good code. And then let's store into the data frame a new thing and go here to stat sig for statistically significant. And let's look at this. And what do you see? There you go. Much better. And you could write this into the all correlations function. If we had more time right here on this, I could go and recode the function to get this to do this. So every time I print my all correlations, I could find the r squared. I could find if it's statistically significant. I could also change how the p-values viewed because I really hate how it looks like with all those decimals. If it's like 0.00, it's basically 0. But with this right here, this is additional information letting us look at it. And now you can tell that this is not statistically significant, and 0.09 is not statistically significant, but 0.047, which that p-value off the screen right there is 0.047, which is only 0.56% of the variation. So this would not be practically significant. Maybe at this point we're reaching some sort of practical significance, but does everyone understand that practical significance is a matter of degree? Everything above here is statistically significant, but we might achieve some sort of practical significance at this level. Like this is where things might come into practical significance, but that's all subjective. Like, is 5% practically significant? Well, it's better than 1.29%. It's better than 0.8%, but everything here is definitely statistically significant. Maybe above here, we can start talking about practical significance. Daniel sent it to me, or I'll send you this afterwards. We'll check it out. But does that make sense how, let me see right here. Daniel's got the code. Let me grab it. Have you created the data frame? Make sure your data frame's created. That looks correct. Oh, you've got it's an open spot somewhere. So your code is open. Oh, you need an extra parentheses. So if you notice when I put that extra parentheses, it closed off. Here, let me drop this in the chat for you, Daniel. You ready? Let me drop this. Dropping this right here. And then let me drop this. Dropping this right here. And Daniel, great job. The real practice is trying to write this out and seeing if you can get it. Like seeing what I write, trying to follow it, and trying to do it. And if your code has an error, then trying to fix it. And every time you catch an error, you learn a little bit more. And then you get to the point where you can try to write it on your own without the steps. It's really like training wheels. So Daniel, great job. Another 50 points right there. Let's hop. Is it working now, Daniel? How's it looking? We'll pause for a moment and ask Daniel if it's working right here. But look, does this look like nice output? Does this look like you could run this for anything you wanted right now? So you could run it for any variable you wanted in this data frame. You could go here to people's height and then just run all your code again. We had it on the data frame stored. So you go here, run all your code again, and you take a look at the data frame, and now you can actually find what it's working. Awesome. And now you look at, we're doing it for height. So we could even change the function, which a little more work than we want to do today on that. So we're not going to go ahead and change the function, but we could. We could if we wanted. Oh, we'll have to take a look. We'll have to take a look. We'll have to figure out what's going on. But you're right on track with it. That's excellent work, Daniel. You're right on track. I'll upload my RMD afterwards. So knowing if someone thinks they're both more attractive, intelligent, and intellect explains about, let me answer that question. So if you wanted to ask about all of those, like you're saying somebody's attractiveness, we got to load up this data frame. Now that is a complex topic. And I'm going to just briefly talk about it. We need the AttractM data set. And so let's load the AttractM data set. I've got the data set loaded. And now you're asking about more attractive, intelligent, athletic explains about, the funnier then. Okay, so we still need the same data set. So at this point, you're asking me for a multivariate model. And this is where I do want to mention. So you're asking how attractive people think they are. And now we would ask for, is it explained by how athletic people think they are? And you said intelligent, attractive. Oh, and then we're doing funnier than. So we're trying to explain funnier than with attractive. And what was the last one? Intelligent. So the most amount of variation we can explain, the absolute most amount of variation we could explain is how much variation in all of this. The most amount of variation we could explain would be what? And this is where we'll be going later in the class. The most amount of variation we could explain in how funny people think they are is how much variation. So this goes to R squared again. The most variation we could explain how funny people think they are is how much. The most variation we could explain how funny people think they are is how much variation. The most we could explain. The most we could explain in how funny people think they are is how much of the variation. Don't worry, it's not a trick question. But the most amount of variation we could explain in how funny people think they are is how much variation. What is the most amount of the variation we could explain? Not a trick question. Pretend you don't know any stats. Be like, how much could we explain if we try to explain it all? 100%, Matthew, exactly right. Not a trick question. So we could try to explain 100% of the variation, or 1 R squared of 1, right? And so if you look right here, if you start adding these, they'll add up to more than 1. That's because variables sometimes overlap in what they explain. Like there's, someone's desired weight and their weight shares sources of variation, so they would explain heights in similar ways. So if we look at this right here, we won't get to 100%, but we will get, and this is showing you R squared comes back to a different R squared. We're at 32.1%. So now knowing the variation in how attractive people think they are, how athletic people think they are, and how intelligent people think they are, that explains 32.1% of the variation. The reason I want to point this out is because this is on the final. So is what you're learning right now important to the final? Yes or no? Chat, help me out here. Go crazy, chat. 20 points, 50 points. Why not? Is what you're learning right now with R squared important for the final when you're making multivariate models? Is it important to learn how to interpret this R squared? Emily is right there. Yes. This is very important because this concept of R squared doesn't go away. It's still 32.1% of the variation in how funny people think they are is explained by the variation in these X variables. This is your Y variable. And then these are your X variables right here. So we're just making a model with these X's explaining this Y variable up here. So this is very important. Yes, sir. I'm not a sir. So this is very important. Great question right there. You can't just add up the R squareds because you will get to more than 100%. And then X's sometimes share the variation. And I should not even show you this, but we can measure the shared variation between the X's with variance inflation factor. More concepts to come later this semester. So all of these concepts are very important because they have big overlaps. So this R squared is not going to go away, and it's going to be a measure of practical significance, R squared is. But we do have correlations that actually happen by random chance that a lot of times people think are statistically significant because they're low, but they're actually happening by random chance. Then we have correlations that happen due to another variable. Why would ice cream sales and shark attacks go up at the same time? It says the answer. But this is called a spurious correlation, which could be due to random chance or due to a lurking variable. So the lurking variable with ice cream sales and shark attacks is what? What is the lurking variable with ice cream sales and shark attacks? Ice cream sales and shark attacks have a lurking variable of what? Of summer. So let's take a look at that. That's the person. I hear them now. So summertime, sorry if I might have to like go say hey to someone because they're fixing a thing real quick. So the summertime is the lurking variable here because think about it. It looks like, when you look at it, that shark attacks increase ice cream sales or ice cream sales might be increasing shark attacks. But in truth, summertime, which is a variable outside of the X and Y relationship, is actually increasing shark attacks and actually increasing ice cream sales. So the ice cream sales is increasing by summer and the shark attacks is increasing by summer. But because of this, it looks like they have a relationship. It looks like ice cream sales increase shark attacks, but they're both just being changed by the Z variable right here. And that happens with other data that we see, such as like age of death and the number of TVs people own. So think about this. The more TVs you own, what? You'd expect people to what? This is negatively correlated. More TVs in a country indicates longer living people. That's positively correlated. What's going on right here with this? More TVs indicate longer living. But this is it says it. I think it's an actual error in the slides right there. That's positively correlated because more TVs in a country would indicate people live longer because it's a measure of wealth. So if someone said TVs make you live longer, it's like, well, no, TVs don't make you live longer. The wealth of a country would have people living longer. We never want to say that correlation proves that something is happening. What is our famous saying? Correlation is not what? Who knows? Correlation is not what? This is a famous saying in all of statistics. Correlation is not this. We can never say prove in statistics. We never say proof. Correlation does not show causation exactly. So you can't say, oh, ice cream sales cause shark attacks. No. And even more so, you'd be like, well, Brian, you can't say summertime causes ice cream sales. You can't. Statistically, you shouldn't. You should say there's a strong association between summertime and ice cream sales. And you'd say there's good evidence to think that they're linked. Oh my gosh. Nice job right there with the jokes right there. So here's another one right here, and this is crazy. Is this correlation very, very high? And let's solve the mathematics on this. This is, once again, tough topics right here, dealing with death on both these slides coming up. So we have right here a correlation of 0.992082, and that's an R squared of 98.4%. 98.4% of the variation in death right here is explained by how much we spend on science, space, and technology. So what's the answer? And NASA, right? Who's with me? No more NASA. We'll save lives if we just end NASA. Well, I hate to tell you, NASA's not the problem. Do you know who the new problem is? The real problem? The real problem isn't NASA. The real problem is Nicolas Cage. Nicolas Cage is highly correlated to people drowning in swimming pools, him appearing in movies. The more movies Nicolas Cage appears in, the more people drown in swimming pools. And take a look, that's a 666 correlation right there. Something bad's going on right here. Not the bees, not the Nick Cage. Less Nick Cage, more people alive. He had the audacity in 2007 to be in 4 movies, and we lost 123 people. Cancel Nick Cage right there. That's definitely this one is causation. This is real data. This is a spurious correlation right here. It's probably just due to random chance. It's a low enough p-value that it's unlikely due to random chance, but it can happen. This lady is like having the time of her life. She's like, she's like, you're Nick Cage. And he's like, yeah. And he's like, can I just get another drink? He's like, I just want to be on my flight. She's like, got her camera phone out. And he's like, hey, YouTube, internet people. So what is a lurking variable right here? A lurking variable is the actual relationship between X and Y. As in, when we look at science and suicides, lurking variable would be time. They're both just increasing over time. Shark attacks and ice cream sales, unlikely. With that emotion. when we look at Nick Cage and people drowning in swimming pools, if she doesn't stop bothering Nick Cage, he may turn her into one of those statistics. Very true right there. Well, Max right there, 20 points. Nick Cage is not going to handle this quite well. But with this right here, what is a lurking variable? A lurking variable is the z variable that is actually controlling the x and the y. It's hidden in the background right there. This right here is probably just a spurious correlation due to random chance. There's probably not a lurking variable. It's just one of those low p-values, as in we think there's a correlation here, but sometimes you get low p-values by random chance. It can happen. Like, what percent of the time does a p-value less than 0.05 happen by random chance? Not a trick question. P-values less than 0.05, which are statistically significant, would occur what percent of the time due to random chance? P-values that are less than 0.05 would occur what percent of the time due to random chance? Not a trick question. It's as easy as it sounds. 5% right there. So 5% of the time, you'll get a p-value less than 0.05. So you might be like, aha, I got statistically significant results. But you could have what's called a type 1 error. We should remember that. Type 1 error is when you reject the null and you say you have evidence, but you don't. So this is probably a type 1 error, unless there's a z variable or unless Nick Cage is really a big problem. He's not. He's awesome. Check out his new movie. Pig, is it? Something like that. So when we do these tests for correlations, we need to look at what would likely happen by random chance. How do you think we're going to do this test for correlation? Great job, William, right there. How do you think we're going to do this test for correlation to see if what we see right here is likely by random chance or unlikely by random chance? We need to come up with some way of looking at this. We're going to get a value of correlation, which is going to tell us the strength, direction. It's positive. It's kind of weak, moderate. The form is mostly linear. No real unusual features, and it's not really got any heteroscedastic nature. It looks to be about the same strength throughout. The R squared is this. If you times square it, you'll get this. So about 12% of the variation in someone's attractiveness score is explained by the variation in their fashion score. Good practice. How do you think we're going to find a p-value for this? The answer is the same way we've been doing. So how are we finding p-values? Take a note right here. How are we going to find the p-value to test the correlation? How are we getting this p-value right here? It says it up there. We are finding the p-value for the correlation by doing what? Running the what procedure? Permutations. And I want you to see this firsthand. Let's take a look at it firsthand right here. We can actually do this. Let's go ahead and take a data set that is super duper correlated. Watch this. You ready? X, 1 to 10. Y, capital Y, 1 to 10. Now, if we plot this, it's going to make a what? Plot here, y goes first in this one. Oh, it's telling me up there what to do. If we plot this, this is going to make a what? X is a vector 1 to 10, y is a vector 1 to 10. What are we going to get when we plot this? By plotting this, Brian will get exactly a what? I'm going to write some new code down here. So we will get a straight line. Boom, right there, you got it. So we can actually get the correlation of this. What's the correlation of this? I think that'll do it. I don't always write this one. I don't do it this way. Yeah, there it is. It works. Good. I don't use those. It's funny. I don't use the simple codes a lot of times. So the correlation is 1 because it's a perfect positive straight line, perfect linearly correlated. And now we're going to go right here. We're going to go to X perm. And now, what are we creating right here? We are creating a permutation of X and Y. So this is just a permutation. Does everyone understand what these permutations are? A permutation is a random mixture of your X and your Y. Does that make sense what a permutation is? We've randomized the X and the Y. So if you were to add a line to this, let's go here to AB line and the LM of it, Y comma Y tilde X. There we go. And let's make it red. Oh, did I put in the wrong spot? Oh, it needs to be outside this. It needs to be here. There we go. Ah, really? Oh, no, I didn't add the X. There we go. So now we've got a red line right there. Yeah, and then that's the permutations. And then guess what we're going to do? We're going to take the same thing here, and we're going to plot for the permutations what we would get for random permutations. So it's the same code right here, but now we're just doing it for the random permutations. How do you think, when I run this code right here, the relationship between the random permutations will look? The random permutations the line will look a lot wetter. When I run this and I look at the random permutations, the line will look a lot wetter. It'll probably look not correlated, and the correlations you're seeing down here, which some could be high, but these correlations right here where my cursor's at, are all closer to what? Just take a look at what these correlations are. If I keep running it, a lot of them are closer to what? Correlations by random chance would be a lot closer. You notice they're sometimes positive or negative. I bet the next one's negative. Wow. The line's a lot flatter because the correlations are a lot closer to 0. These are all random chance permutations right here. And this is what the procedure is doing in the background. And it's tracking all of these numbers for us. Some of them are kind of high. It's possible. Ooh, that one. Ooh. That 0.721, that was really high. That's this one right here. This was by random chance. So when we run the association procedure, it's going to do all of that for us. We can actually run the association procedure on Y and X and take a look. It's showing us that our correlation for the Pearson was what? Remember, just look at this. This is what this represents right here. We're connecting the graphic. Our correlation is what right here? What was the value of our correlation? That's what we see right here. So what's the value of our correlation? That's the strong red line right here. 1. What is a correlation just as extreme as this? What is a correlation just as extreme as 1? So this is our correlation, and this is a correlation just as extreme as 1. -1. Does that make sense? So it's showing something just as extreme over here. This is what we observe, correlation of 1. Then we observe something just as extreme, and can you tell me the p-value? The p-value will be the percent of random permutations. These are all the permutations I was making, and now it's recording the values for us. The percent of random permutations outside of this is how much? The estimated p-value for this would be what? How many random permutations look to be as extreme or more extreme than our results? Who knows what the estimated p-value would be? Oh, Megan, that's 50 points. I was going to mention that next. 0%, and that's what the estimated p-value is going to be up here. The estimated p-value is 0, and there's the estimated p-value. And are you confident? Yes or no? Are you confident? Yes or no? Are you confident that it is statistically significant? Yes or no? The p-value is estimated to be 0, and are you confident about it being statistically significant? And why? Very confident, because the interval does not contain 0.05. And Megan pointed out that looks like a normal curve, and now look at it. Let's make it really awesome. If you look, if I increase the permutations right here, you actually get an even more normal shape from it. And I just wish it would look so perfect. But you get this normal shape, this normal histogram right here, because of the way the procedure is done, and actually is mimicking what we do on our normal procedures. So it's actually creating basically a normal curve, and we get that. And we might have finally had one permutation as extreme. No, we're not getting any as extreme or more extreme than our results. That's weird. I thought we'd get one as extreme. But no, we're getting no results as extreme or more extreme than our results. Yeah. And it's estimating the p-value to basically be 0. So this is showing us that we have strong evidence that our Pearson correlation, the linear correlation, is very, 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 very statistically significant. And that's what we're going to see in the notes right here. We're going to see the exact same thing. So we're going to randomly permutate the x and the y. Now you can permutate 1. It's like this. Would your grade be random on the test if I tossed your papers up in the air and I said, grab the paper closest to you? Would your grade be random then? If I tossed your grades up in the air and I say, grab the one closest to you. So that's mixing up the y. I'm mixing up your grades right there. So would your grade be random then? If I toss your papers up in the air and say, grab the one closest to you, I'm mixing up the y variable. Would it be random? What's in my sin? You would have a poor estimate. If you're talking about models, there's overfitting and underfitting for models with the amount of variables you include. Whitson, if you're talking about models, models will have too many variables or too few variables and be over or underfit for models. Permutations, if you don't run enough, will create a weak estimate or a stronger estimate. You can't run too many permutations because it just takes more time and it makes better estimates. Good question, Whitson, right there. My grade would be great because your students are on, Daniel. Thank you. So your grade would be random, though. And if my students are awesome, which I do hope and I do believe, then your grade would be great. But if we were to say, how about I toss your grades in the air, that randomizes this, and then I tell you to switch your seat, would your grade be random then? So if I say, I'm going to toss the grades in the air, so I'm randomizing what the grades are, and then I say, okay, now sit in a random seat and grab the one closest to you. It's still just random. So you notice right here on my example, I permutated my X and my Y. That's random, but I could have truthfully just permutated the Y and it would break the relationship between X and Y. I like to permutate them both. It's just the way I roll. So right here, you'll notice we have the correlation we observe and the correlations by random chance. Correlations by random chance are oftentimes closer to what? Key note right here, a correlation by random chance would be closer to what? Key note right here. Like, it's just a good note. A correlation by random chance would probably be closer to what? 0 right there. What's in your right? Shiv, great answer right there. Our correlation looks to be very strong. So when we look at the result right here, it's important we know this is our observed correlation. Who can explain what the p-value is? This is what you want to see in your notes. That is the p-value total. So p-value. And now this over here, as extreme, that's as extreme as what we observed. It's not what we observed. We did not observe a negative correlation, but negative 0.94 is just as extreme. And then the p-value would be the percent of permutations that are as extreme or more extreme than our permutations, or one just as extreme, occurring by random chance variation. And thus, these right here are very important to note. All of the histogram right here are your permutations. Those are all the permutations right there. The permutations are the histogram, and you can see this. Let's go check it out. It's very clear to see these are the permutations. If we go inside of here and we just run something like permutations equals to 3 and take a look, can you see the 3 permutations? Or change it to permutations equals 1. But why, and this is a good note to have, why do I have this and this? Who can explain for 100 points why I have this right here with 1 permutation and I have this over here with another 1 permutation? What's going on with here's 1 permutation for this and here's 1 permutation for this? This is what we've been talking about all class right here, which is linear correlation. So what do you think's going on? Why you have this? It's important to know what you're seeing in your output. Here's histograms of the X, a histogram of the Y variable. Here's the bivariate scatter plot relationship. These are called border histograms, just letting us view the univariate of X and the univariate of Y and the bivariate relationship in the middle. So what is the deal with this down here where we have chance values of Pearson, which is what we've been talking about all class? What is this over here, which we'll be getting to in a moment? What is this over here? It looks like it's a whole nother what? Who knows? 100 points on the line right here. Who knows? This over here would be a whole nother what? A whole new something. I can't appear. I'm drinking my coffee. What is that? Oh, Megan, you got some knowledge right there. People seem to know. Maybe people are Googling Spearman in the background. It's quite a whole new world. It is a whole new test right here, a different type of test, a different type of correlation. There's Pearson correlation and Spearman correlation, and Megan is right. We will use Spearman correlation for nonlinear things with outliers, and we'll see that here in a moment. So great job. Spearman is used when we have nonlinear relationships and when we have outliers, because Spearman will downweight outliers. We'll find out more about that in a moment, but it's a different type of test. So when is Pearson appropriate? Take a look. Pearson is appropriate when you have QQ straight enough, no outliers. What's the problem here? Outlier. We also don't want heteroscedastic relationships. What does heteroscedastic mean about the spread? Heteroscedastic relationships, which I've covered there in blue, we want the green one right here that is homoscedastic. What does heteroscedastic versus homoscedastic mean? I read the description R once. Nice. Megan, you're totally right. That's what it is. It's when you have outliers, you want to use Spearman. Great job. I'm throwing another 100 points. That's great job, Megan, right there. R can help out a lot. So when you see right there, varying spread, perfect answers right there. A+ answers today. Nice job. Homoscedastic means same spread. Like think homo same. So hetero means different. So I mean, just like, heterosexual attracted to different sex, homosexual attracted to same sex. And so when you have same spread, homoscedastic, same spread, heteroscedastic, differing spread. So you can see right here a heteroscedastic relationship, And you can see right here a homoscedastic relationship where the spread is the same. We're talking about the thickness of the line is the same throughout. When it's heteroscedastic, it spreads out like this. So heteroscedastic, so if the data kind of looks like a funnel, and you could have it look like a funnel, or great answers right there, Max. Great questions and answers. You could also have a heteroscedastic that looks something like this. It just has to have differing spreads. Does everyone see here? It looks like a clock, or like, what is those things? What are those? I don't even know what it's called. But it looks where there's differing spreads, and you can check to see if the strength changes throughout here by going here and doing the following, and you can see it's a heteroscedastic relationship. An hourglass, that's what we got right there. Couldn't remember the name of it. Looks like an hourglass right there. Everyone's paying attention. You got it. I just gotta be like, I don't know what this is. Simple things, and you just help out right there. I love it. Great job, Kevin, Matthew, and Megan. But there's a differing spread right here. The thickness is not the same throughout. You don't want to see that. That's not good. We want there to be minimum heteroscedasticity, and we don't want there to be extreme outliers. So if you do have things like extreme outliers, that's going to be a problem because outliers can change the correlation. We do have ways of handling that, though. So you've been seeing me run this code today, and we ran it last class. What's really great about this is whatever class you have for your x and your y, it'll change the associate function. Now, you probably want to use a seed, because if you use seed and you knit, it will do what to your randomness? What will it do to your randomness if you use seed when you knit? Because this is based on a randomness procedure. The permutations are generated via randomness. So if you use a seed, what will happen to your randomness? Every time with that seed, you will do what? Which is good to do. Even if a question doesn't say it, I'd throw a seed on there. It's like in Minecraft. It'll make it so it can be recreated. Your results will be reproducible. So a seed sets the randomness. You get the same results. Great answers right there. So I would definitely throw a seed on anything you're doing, unless you want the randomness, just to show you. The reason we use seed right here is if I run this, and you can just see this permutation jump around, it's going to do different random permutations each time I run this. So you can just see the bouncing around of that one permutation, but as soon as you set a seed, and Rock, does it matter what the seed is?
It doesn't matter!
Nope, you can just put in whatever number you want. It's just like a code to set the randomness. And now every time we run it, same thing. So you can put in your favorite seed if it doesn't specify a seed, and just choose right here. Let's do some leet seed right here. Whatever you want. And then you choose that seed, and then the randomness you get will be the same. Now the results change because I changed the seed, but now when I rerun the code, it doesn't change unless I set the seed to nothing. I think that will not set the seed, yes. The seed is now missing, which is the default. Don't set your seed to NA. That means there is no seed. The seed is missing. So with no seed, we get random results, but with a seed, we get a consistent result right here. It is random, but we are able to reproduce the random results. Good stuff right there. We got this. So here's a result right here. Positive correlation, moderate. We've got here mostly unimodal, a little bit of bimodality in somebody's fashion score. Positive, it's pretty good. Pretty good. Little, not too heteroscedastic. Pretty good. Pretty good. So what would you think the p-value is? Let's say I had you estimate the p-value. Quick question. I would love this as a text question. Possible p-values A, B, C, or D. Let's go right here. I'm going to throw you 200 points. Let's see who my people get. A is going to be 0.001. B is 0.005. C is 0.008. And D is 0.06. What do you think the p-value is? I'm trying to be tricky on this one. If you want to find the p-value, you look at it. I'm going against the conventional logic. See how close I was, my guess. Veda, you are not tricked. Veda's getting it right there. It looks about maybe 60%. I might be off. I might be off in my guess. But you're trying to figure out what percent of that curve is shade or as extreme or more extreme than our results. Veda, I said 200 points. Great job, Veda, right there. Getting some massive points. Make sure our hashtags show up. And so, look at that. Look at that. Not, I said 6%. Decent guess. Look, I mean, the estimated p-value is somewhere between that. So when we look at the results right here, this p-value right here, which we're getting, is 4%. So in truth, see, I should have went a little bit lower. I tried to trick everybody. That p-value right here is 4% because that's the amount of shaded area there is as extreme or more extreme than our result. That's why it's 4%. It was just a guess. It was looking at this right here and saying how much of the total curve. The curve is 100%. Think of it as like a cake, and you go into this cake, and you go to the cake and you eat this portion of the cake off the cake. How much of the cake did you eat? So do you notice right there how I'm shading it? I'm shading it similar to that, Megan. I'm looking at the cake and I'm saying how much of that cake did Brian eat? And the answer is apparently about 4%. It would be sometimes it's easier to guesstimate, but I've ate about 4% of that cake. That's the results that are as extreme or more extreme than our result. The good thing is we don't have to estimate it. It's going to show us the graphic, and then we will see that it was 4% right here. Like it was 4%. The other one's pretty similar at 5.6%. And then what do you notice about these intervals? Both of these intervals would tell us that we are what for our results. The p-value is outside the curve, so it's just the test stats we learned. Yeah, I think so, yes. The p-value is just going to, I think so. Good bet there, Whitson. I think that is correct, Megan. I think that is correct. Clarify if you want. And these p-values are inclusive of 0.05. So what would you tell somebody who ran this results right here? That's down below. Since the p-value is inclusive of 0.05, we can't tell if it really is statistically significant because we think it is. We think this one is. We think the bottom one is not. But we're really not that sure because we're like, well, it could be. It might not be. Both of them. Like we think the first is, but it might not be. We think the second one's not, but it could be. So the way we do this right here when we have inconclusive intervals, because these are inconclusive, review right here. We have inconclusive intervals. And since we have inconclusive intervals, what do? Since they're inconclusive intervals, we will do what? We're like, I don't know. Maybe it is. Maybe it isn't. I don't know. Hard to tell. It might be. It might not be. I don't know. Yes. Oh, yeah, you're saying it makes more sense that we're saying how possible it is by random chance. That's exactly it. Yeah. That's what a p-value is. It's telling us how likely this result would be by random chance. And that's what the permutation procedure does. It shows us what we see by random chance, and then we can find out how likely our result is by random chance. So that's why we're saying this is the probability of our result or result more extreme happening by random chance variation, given that there is no correlation right here. Because the most likely thing to see if there... Megan, great job right there. Yep. The most likely thing to see if there is no correlation, that was meant to be an arrow down to that, is that there is no correlation. Because that's the most likely thing to see if there is no correlation. And if we come back with an inconsistent result, we need to increase those permutations. Yep. I like Megan, you're seeing it right there. Yeah, it's like, oh, that's literally what it's showing us. It's showing us if this result was likely by random chance, by generating random chance results and telling us how probable it is by random chance. When you see it, and you're like, oh, that makes sense what a p-value is. It's just, this was likely by random chance, this was unlikely by random chance. What values of correlation would have a high p-value? What values of correlation would have high p-values? Good. I love this as a possible, like, just quick question. What values of correlation would have higher p-values? What values of correlation would have higher p-values? Values of correlation that would have higher p-values would be what? And the answer is inside this graphic. Values of correlation that would have higher p-values would be what? Values of correlation that would have higher p-values would be what? Values of correlation that have higher p-values would be what? Basically, Max, you're saying they'd be closer to 0, right? Max, you are correct right there. So they'd be closer to 0 because that's more likely by random chance. The ones that are most likely by random chance are the ones at 0 or around 0. So if we observe a correlation close to 0, then that's more probable by random chance to get a small correlation. The correlations that are less likely by random chance, which we kind of have here, are the ones that are bigger in magnitude, as Max is saying. Great answer there, Max, from 20 points. And so the ones that are further away from 0, bigger in magnitude, are less likely by random chance because it's unlikely that they would occur. Just if you look at what happens by random chance, and we get the random chance through the permutations. So we have a last way of looking at correlation right here. And the last way of looking at correlation is what is called Spearman correlation. Now, when you think of Pearson correlation is only for what versus Spearman correlation over here? Pearson correlation is only for what type of correlation? Pearson correlation is only for what? I should draw my Spearman a little bit differently. There we go. That's a good Spearman. Pearson is only linear. And Spearman can be used for what? That's a Spearman right there. Here's a Pearson. Spearman can be used for nonlinear, and I had to redraw it for a moment because here's an important note. Spearman would work for this one here, but Spearman should probably not be used for this one here. Now that kind of looks like an S2, but what's the difference between the red S and the green S? And this is a good review topic. What's the difference between the red S and the green S right there, which they're both kind of weird S's? What's the difference between the red S and the green S? I want to point out some parts of this, and this is an important thing about Spearman. This is a bad red S, and this is a good red S, right? Green S right here. The green S, Wilton knows exactly what I'm trying to point out, is that the green S is monotonic. It goes in one direction. So Pearson is for linear and widen out at the ends. Yeah, we don't want a lot of heteroskedasticity in Pearson. Your best Pearson ever, if you want to think what Pearson's going to look like, your best Pearson, I'm going to delete some stuff on this slide right here. This right here is what you want to see with Pearson right here. That is Pearson. So that is Pearson when you have a general homoskedastic relationship without any strong outliers, like that one point outside there, not really an outlier. Homoskedastic, no strong outliers, so you just have a good stream of points. And you'll see right here, this one, it's pretty good. It's pretty good right there. Not so bad. Whoa. Like spinny right there. That was a joke right there. I'm sorry I didn't get it. I'm sorry. But Spearman is going to help. Spearman's going to help deal with some of these problems right here that we have. So which of these would Spearman apply to? 1 or 2? Which of these would Spearman apply to? Which of these would Spearman apply to? Graphic 1 or graphic 2? No. Graphic 1. Spearman applies to monotonic. We're not going to use it on non-monotonic. We're out of luck on non-monotonic. We're just not going to deal with it at this moment. There's ways. There's always ways. So when we look at the Spearman relationship, here's what happens. We take all the values and we turn them into ranks. So I want you to just think about this theoretically right here. If we were to have 3 data points, and the data points were to go from 0 to 100, and maybe like 0 to 10. It's a weird scale. And then we had this data point here, this data point here, and this data point here. Do those follow a line? Do those values right there follow a line, yes or no? Because this could be at like close to x0, y0, x10, y4, and x100, y6. Do those follow a line? Does that follow a line really well? Is that a linear pattern of data, yes or no? I would say no. But watch this. Let's go here and mark that this right here is the what on the x scale. If you go from left to right, this is the what x. I would say it's not that linear. Like it doesn't follow a line very well. It's not linear. It does go up consistently, but this would be the what x. If you go from left to right, from the smallest to the largest, this would be the what. This would be the what x on this line. This one right here. If you rank it from smallest to largest. Oh, no worries. Yeah, message me, Nathan, afterwards, and I'll make sure to do it. So what x would this be right here? This would be the what x. From smallest to largest, it'd be the what x. This point right here. That'd be the what x. It'd be rank 1, smallest. How about this one? This is rank 2. How about here? This is rank 3. Now, if we go from smallest to largest on the y, this is the smallest y, this is the second smallest y, and this is the third. What do you notice about the correlations of the ranks? If we go over here and plot the ranks from 1 to 3 and 1 to 3, the Spearman correlation for this would be what? What do you notice the Spearman correlation of that would be? The Spearman correlation would be 1, because the Spearman correlation takes the values and turns all the values into their rank, which is just least to greatest on their respective scale. Does that make sense what you're seeing right here? You're just seeing, okay, this right here is the biggest X, so it's 5. This is the biggest Y, so it's 5. This is the smallest X, so it's 1. So we're taking the values and turning them into ranks. So what happens to outliers? What is the highest possible value of X and Y right here these could be? The highest possible value of X and Y that could exist for these 3 data points is what for X and Y when we turn them into ranks? Just think what's happening theoretically right here. The highest possible values for X and Y. So Spearman and correlation is not quite linear. It will do linear, but it's doing the linear correlation between ranks. So it is, exactly, Megan, you could only get as high as rank 3 for each of them. So what happens to extreme values? It doesn't matter.
It doesn't matter.
If this is a billion right here, like if I were to change the scale to this, that the actual values right here are like 1,000, I'm running out of room, it's not going to change because we're going to turn it into the rank. Does that make sense how this is going to, outliers are not going to impact it? Outliers are not going to dramatically, or they just have no impact on Spearman because we're going to turn it into a rank, which then if it's the highest value, it can only go up to how many values there are in the data set. For this, we're only looking at 3 values. There's only 3, n equals 3 right here for this. For this example, great answer right there, Nathan. For this example, the highest value, if there's 5 observations, the highest value would be 5. They were just put in the context of the data, so large numbers don't have the influence. Exactly. Large values can influence it because it's going to be the rank of the number. So Spearman turns them into ranks, which downweights outliers. It deals decently with heteroscedasticity because the differing of the spread is not going to really matter as much because extreme differences of spread are going to be downweighted also. The best thing it deals with is the outliers. So when we look at this right here, we're looking at the rank correlation, which is actually the linear correlation of rank, but we're seeing right here the Spearman rank correlation. And I want you to look at this right here. Would you use, and this is a pretty easy test question, if you were asked on the test, would you use Spearman or Pearson right here? Which one would you use for this graphic and why? Yep. Great answer right there, Nathan. Yep, that would be correct. 20 points right there, Nathan. Would you use Spearman or Pearson and why? And you want to draw the form through it, and the form looks like that. And the answer is most definitely what? Put the 2-minute warning on. 2-minute warning. Exactly. And so Shiv, I'm going to throw Shiv some more points. It is monotonic, but it's also what? And Megan's got the extra. We can use Spearman because it's monotonic, and we should use Spearman because it's not linear. All lines will be monotonic. So Shiv, you're on the right track with that right there. We want to use Spearman because it's not linear. Pearson, if it is linear, which we have on the previous slide, if it is linear, we'll use Pearson. If it's monotonic, non-linear, we'll use Spearman, which can help us deal with outliers and heteroscedasticity. And I think that's it. That's it. This is just making graphics. Let's look at one more correlation. We got just enough time to go look at it. Let's go look at it. Let's run a association on this right here. Let's see which one we should use. Association on this, tilde, this, data equals. Okay, so I want to know what I should use right here. We got just enough time to look at this. Oh my gosh. Oh, but it's actually correlated? Really? Wow. That's a big mess. That actually has so what would the answer to this be? That's crazy. I'm going to look at this one other way. We're running out of time. We've got seconds to go. I want to see it another way. Well, yeah. What should we use for this? Last question of the day, 100 points. What should we use for this? It looks crazy, but it's actually not that bad. What should we use for this? This would be a pretty easy test question if you know which one to use. Which one would we use for this? That is Pearson. That is Pearson. That is a linear relationship, no extreme outliers, and actually it exhibits very good, and that's the end of class. It exhibits very good what? So last class is over. Let me put this up. It doesn't have extreme outliers, so we don't want to see the extreme outliers. Let me make that box even smaller. Also, it exhibits very good what? So there's not extreme outliers. You're like, oh, that's outliers. I don't know. Nothing too extreme. It exhibits also good what around the line, which this is very good. This is a very, very good, higher than I expected correlation. No extreme outliers. Nothing too bad going on. A little bit of weirdness, but nothing too bad. But also, we look at this right here and we say it's got very good. I'll tell you, it's got very good this. I'm trying to tell you it's got very good what right now. By doing this right here, I'm trying to say around the line, the strength is consistent. The strength is consistent throughout the model. The correlation looks to be about equal. We're putting that in as a joke. Megan right there, coming up with some ultimate jokes right there. Almost good as Dissy right there. Another few points right there. Wilton, great job. And really good job. We finished off the notes today, which is exactly where I wanted us to get to with all the craziness. Sorry for all the... I'm going to go see if they fixed what I asked them to. Man, I tell you, living in this COVID world is not fun. Who would have thought it's fun? Not me. I know. I think that's excellent right there, Megan. So should we use... I think so right there. Let me see what Max wrote. So we should use Spearman if there's outliers, nonlinear, heteroscedastic, must be monotonic. Use Spearman if... Let me add to what Max wrote right there. And then for must be monotonic. Use Pearson if... No, excellent work, everybody. I really mean it. Like, it's... Imagine if... Oh, we're going to go this song right here. I like this song better. Imagine if, like, no one talked. That'd be so sad. So every time you hear talk, I love it. The hardest classes for me are the classes no one talks. And I really appreciate it because it makes it fun. I want there to be interaction. I don't want to talk to myself. I want to talk. I don't know how to spell outliers. No outliers, mostly homoscedastic and linear. No big outliers. Okay. So there we go right there. Use Spearman if there are outliers, nonlinear, or homoscedastic, must be monotonic. Use Pearson if no big outliers, must homoscedastic, mostly homoscedastic, and must be linear. It's so fun. No one talks to my Zoom classes. Oh no, I'm sorry, Megan. I'm sorry. I'm sorry to hear that. I have off stars at 145, right? Our attendance got a little bit better. It got up to 30-ish today. I'll take that. I'll take the win right here. I'll take it. 30-ish. Better than 20-ish. You take what you can get. And then you... something's facts of life. Thank you so much, Megan. It makes my day. I'm glad people like this class. NFL Fast R? Actually, maybe I have. What is that, Max? Send me that stuff on that, especially Discord or put it in the fantasy thing. What is the NFL Fast R? Because there's a whole bunch of stuff on R and fantasy and all these different things. And the Big Data Bowl. Watch out for liars. I'm putting it as a joke, Megan. Megan, we need more jokes, and Megan's throwing down those jokes. Mubot knows these jokes right now. Keep throwing those jokes. I think you're the only class who knows about Mubot's jokes, and that's thanks to Megan right here. Megan getting some good jokes for us right here. You can always ask for Mubot to do a random joke. And what's really cool is that going forward... Did I do it wrong? There we go. Oh, he actually did it. He actually chose that joke at random. It's a set of functions to scrape NFL data. I think it's what people use for the Big Data Bowl. Max, we need to do this. It's NFL Fast R. I need to go see what they did. You can't tell me about something cool and then I'll... Okay, let's go check it out. Max telling some cool stuff right here. Okay, looks like we have it. Did you mean... Oh, look, it's correcting me. It's like, did you mean this? I probably did. So we're downloading this package that Max is telling us to right here. This is on the CRAN server. We're going to load this package right here. We got fast models, XGBoost. Oh, XGBoost is where it's at. That's extreme gradient boosting. Fast R models, I don't know fast R models, but XGBoost is extreme gradient boosting. Great job, Megan. See you next class. And so extreme gradient boosting is using like gradient boosting models, which have a lot of tuning parameters. There's so much I could tell you. We'll cover that in 474. But let's go look at this really quickly, really quickly. Build NFL Fast R PBP. Fast Scraper. Here we go. Fast Scraper roster. Okay, let's go. Fast Scraper schedule. Can you combine my points? Yeah, email me, and I will combine points. Fast. They probably have an example. They might have an example. Whoa, cool. I love it when they do that. This is so cool how they do this. Oh my gosh. Holy mackerel. Okay, wait. Fast Scraper schedules 2020. Okay, 2 accounts and all this good stuff. I think we've done it. Team colors. I don't know. Oh, wait, no, we need to go back here. Look at what we just got, Max. In a matter of seconds, we just scraped and what did we get? Play ID. Oh, these are the players? Player ID. I think this is all the... Oh my gosh. What? This is all the players. And we just got all this data right here. Oh, it's per play. We just got all these plays. We just got all of the plays right here from maybe a certain amount of games or something. So this is each play in a game, it looks like. And so we scraped from the 2020. I'll have to look at what we're doing right here. From 2020, the tail 3, the last 3 games. I think we just scraped the last 3 games of 2020. So let's scrape the last. This might be the last game of 2020. If I'm correctly thinking what we're doing right here, we just scraped the last game of 2020. Was the last game of 2020, is this the Super Bowl? Tampa Bay, right? And we can see the last play in the Super Bowl. If we go all the way down here to the end, there were 184 plays in the Super Bowl. And this looks to be it right here. The last play might be this. I think it's by play. And there's the time on the clock. Yes, so we just scraped the Super Bowl. And decision at the end right there. It looks like decisions end of game. QB kneel. Brady took 3 kneels at the end of the game. We just literally scraped to the Super Bowl in seconds. So you could go back here and ask, like, let's look at the Super Bowl for 2018. If you want to see the Super Bowl for 2018. So I think I just loaded it up. The last 2 plays of the Super Bowl, LA versus New England. Oh, did New England lose right here? The last 2 plays of the Super Bowl. You go right here, QB kneels, QB spike, and a field goal right there. But there you go. There's the last 2 plays of the Super Bowl for 2018, and we're getting this in a matter of seconds by just scraping, and then the tail is taking the end of that right there. This is really cool stuff, Max. Well worth the 100 points I'm giving you right there. But just seeing how this code is running right here, it's piping it through into a fast scraper too. I don't know why. We're using fast scraper schedules to pull from the year 2018. That's like how fast scraper schedule works. Then we're pulling the tail of the year 2018 because we're passing that through to the next object. And then we're passing everything there to the fast scraper, which seems to know how to take that data. Really quick, really easy. So much cool stuff you can do with this. I might even be showing this to my time series class here today. I'll be back here, Max. Great job. Really cool stuff right here, what you can do with this. Just a little bit of knowledge on the coding. You can be like, wait, what's this going to do? And you can see we get the ways of using it down here. So really cool output. We'll be back, everybody. I'm going to see if they did what we asked. I'll talk to everyone later. Bye for now. Bye.